This will be the final part of the lecture over chapter 21. We'll be dealing with sections 10 through 12. We're going to look at magnetic field energy, and we're also going to look at RL and LC circuits. An inductor with inductance L carrying current I has a particular energy, 1/2 Li squared. This energy is stored in the magnetic field of the inductor. The energy density, or energy per unit volume, is going to be given by B squared divided by 2 mu naught. And then RL and LC circuits, we're going to look at some of the components here, but the summary is pretty much in a circuit containing a resistor and an inductor and a source of EMF. The growth and decay of current are exponential with a characteristic time t called the time constant. It's given by this. The time constant is the time required for the increase in current to approach within a fraction, about 63% of its final value. The time dependence of the current is given by this. A circuit containing an inductance L and a capacitance C undergoes electrical oscillations with angular frequency omega, where omega is given by this. What we are seeing here is when an RL circuit, when the switch is closed, we can see as time increases that there is a certain amount of time for it to get within the current to get within 63% of the steady state value. And this is what the time constant is going to be referring to. So let's take another look here at section 2110. Establishing a current in an inductor requires an input of energy. So an inductor carrying a current has energy stored in it associated with its magnetic field. So a changing current in an inductor causes an EMF between the inductor's terminals. The source that supplies the current must maintain a corresponding potential difference between its terminals while the current is changing. Therefore, the source must supply energy to the inductor. We can calculate the total energy input U needed to establish a final current I. And let the current at some instant be I, and its rate of change be this. Then the terminal voltage at that instant is going to be this. The average power is going to end up being this. The energy supplied to the inductor during the time interval is going to be this. So the change in that energy is going to end up being this. Bottom line, the energy stored by the inductor ends up being 1/2 Li squared. Any ideal inductor has no resistance and dissipates no energy when carrying a current, and it only stores energy. The result can also be derived with calculus, but we're not using calculus in this course. We won't worry about it. After it reaches its final steady state value, then the change in the current becomes 0 and the power input is 0. We can think of the energy U as analogous to a kinetic energy associated with a current, and this energy is 0 when there is no current, and when the current is I, then this is the energy. When the current decreases from I to 0, the inductor acts as a source, supplying a total amount of energy, this, to the external circuit. If we interrupt the circuit suddenly by opening a switch, the current decreases very rapidly. The induced EMF is correspondingly very large in order to try to compensate, and the energy may be dissipated in an arc across the switch contacts. And this large EMF is the electrical analog of large force exerted on a car that runs into a concrete bridge abutment and stops suddenly. So the energy in an inductor is actually stored in the magnetic field within the coil, just as the energy of a capacitor is stored in the electric field between the plates. And as we go through and we develop the self-inductance of a toroidal solenoid, We come up with this. We know the stored energy U and the current is this. So basically we take this, plug it in here, and this is what we get. The magnetic field and therefore the energy are localized in the volume here, enclosed by the windings. The energy per unit volume is this. And then, so the energy density is going to be this divided by the volume, and turns out to be this. So we can express this energy in terms of the magnetic field inside the toroid. And basically we can rewrite a lot of these terms using the term B, and this is what it turns out to be. And if you have certain values, you can plug it in, you can determine what the inductance happens to be. So if we're looking at inductor energy, let's say an engineer connects a 0.04 Henry inductor to a power supply and then ramps the current through the inductor as follows. Which of the following represents the changes in the potential energy stored by the inductor? Well, we can use equation 21.18 to calculate the potential energies at the three given currents. Since the energy is proportional to I squared, so that the potential energy at this is the same as this, the correct answer ends up being C. So now let's go to the RC circuit. So an inductor is primarily a circuit device. A circuit contains a resistor and an inductor and is called an RL circuit. Let's look at the behavior of one of these circuits. We aren't going to see any sudden changes in the current through an inductor. This equation shows that the greater the rate of change of the current, the greater must be the potential difference between the inductor terminals. This equation, together with Kirchhoff's rules, gives us the principles that we need to analyze circuits containing inductors. So if we look at a circuit, the resistor may be a separate circuit element, or it may be the resistance of the inductor windings. Every real life inductor has some resistance unless it is made of superconducting wire. When you close a switch, we can connect the RL combination to a source having a constant EMF. So let's say it's initially open, then at some point T, it's closed. As we've mentioned, the current cannot change suddenly from 0 to some final value because of the infinite induced EMF that would result. Instead, it begins to grow at a definite rate that depends on the value of L in the circuit. So we're going to let I be the current at some time T after the switch is closed, and then let this be the rate of change at I at that time. Potential difference across the inductor is going to end up being this, and the potential difference across the resistor, of course, is this. Applying Kirchhoff's voltage rules, basically we're not having voltage stored up at any particular point, therefore the voltage drops on these two and then is equal to 0, at least as far as the difference between the EMF and those. Solving this equation, we find that the rate of increase in the current ends up being this. At the instant the switch is closed, I is equal to 0, and the potential drop across R is 0, then the initial rate of change of the current is going to end up equaling this. Basically, this term falls away. The greater the inductance, the more slowly the current increases. As the current increases, the term R divided by L times I also increases, and the rate of increase of current becomes smaller and smaller. When the current reaches its steady state, then its rate of increase ends up being 0. So in other words, the change of charge of current with respect to time is equal to 0, which means that this arrangement is true. And then the final current ends up being I is equal to E divided by R. So for a battery-driven RL circuit, we can see the current as a function of time. And we can see the graph of this. It's an exponential graph that eventually gets up and approaches this particular value. We went over the time constant, and This time constant is going to be the inductance divided by the resistance. You can see a few problems there that you can go through and work. Energy considerations offer additional insight into the behavior of an RL circuit. The instantaneous rate at which the source delivers energy into the circuit is going to be this. The instantaneous rate at which the energy is dissipated is going to be this. And the rate at which the energy is stored in the inductor is this. When we multiply equation 21.22 and rearrange the terms, we come up with this. This shows that the part of the power EI supplied by the source is dissipated in the resistor and part is stored in the inductor. So now let's move on to the LC circuit. So this will be section 2112. It's a good album. So a circuit containing an inductor and a capacitor, which we call an LC circuit, shows an entirely new mode of behavior. So in other words, rather than have the resistor in there, you've got a capacitor. It's characterized by oscillating current and charge. This is in sharp contrast to the exponential approach to a steady state that we see with the RC and the RL circuits. In the LC circuit, we charge the capacitor to a potential difference, any initial charge of this is shown here, and then close the switch. So what happens? Well, the circuit's energy all stored in the electric field. You've got a capacitor that's fully charged. And then as the capacitor is discharging, then you have more current. And the circuit's energy all stored in the magnetic field at some point at T is equal to 1/4 of the period there. Then the capacitor is again fully charged as the current went back this direction. And then you can see here that the circuit's energy is all stored in the electric field here. And then as the current tends to flow backwards again, well, in this particular case, it went from here to here, and now it's flowing backwards. You can see the current's energy is all stored in the magnetic field. And that particular type of oscillation goes back and forth. So you're seeing the current start at 0, eventually build back up to I max, and then go back to 0 again. And then you can also see that the charges here, you start with positive Q max, and then as the current flows, it's 0, and then it will eventually go to minus Q max, and then back and forth, and just continues to repeat. Omega here, the angular frequency of the oscillations ends up being this. We're not going to go through the derivations here. But here's an application of what's going on. When you use the tuning knob on the radio, this type of radio, the radio is going to use an LC circuit to tune into one desired frequency among all the other frequencies. The radio waves creating small oscillating currents in the antenna. And a given LC circuit is most responsive to currents oscillating at its own resonant frequency. It tends to pass frequencies close to this and screen out the others. So when you twist the knob, you're changing the capacitance or inductance of the current of the circuit, and thus the resonant frequency. So that is an application of this particular type of circuit. So I hope you got something out of all of this. Again, inductance is one of those things that you may not think that much about, but it does play a pretty big role in everyone's lives.